And go live.
Live?
Yeah.
We are live. Can you check
Go live.
Sahil?
Yep. We're live.
All right. Wait, is there echo?
No, you're good. I
Oh.
usually have to mute my thing. You're
Okay.
good. Yeah.
Okay. All right. Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
I'm Mikey.
This is Sahil. Welcome, everybody, to a brand new, exciting episode of Corecast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So last time we had talked about maximum entropy in the sense of like, what is there a limit to how much entropy you can have in a certain amount of space? We talked about how that relates to black holes. So if you are interested, do check out our last episode on that. We go into the nitty-gritty of that. But here, I want to ask a converse question of a minimum entropy. So I guess, Tim, can you start off by describing, like, classically, how do you think about minimum entropy? What does minimum entropy even mean?
Yeah. So last time we talked about maximum entropy is a black hole, and that's what happens when you start stuffing more and more stuff into a system. And we describe how entropy is just counting the number of possibility. And the converse of that is when you kind of start to remove possibility. One simple way to do this without removing actually stuff is to just lower the energy. When you lower the energy of a system, there's kind of a fewer currency to do stuff. And this is, and in everyday life we experience this. For example, when you take water, put it in the freezer, as it cools down, and it, roughly speaking, becomes a little more ordered because it turned into a lattice structure. So we know that the easiest way to reduce entropy is to just kind of cool your system down and just kind of suck away all the energy that it can use to do things. And that's how you can reduce the entropy. And at some point, when you reduce it more and more and more, you will eventually end up with a lowest entropy state, at least given the system that you have.
Gotcha. Actually, one question to that is, like, say you have a gas of particles and you reduce the energy, so I would think intuitively they move slower. It doesn't, I don't know, would that impact the entropy? Because the number of possible configurations of a fixed number of particles in a gas of particles in a box still seems to be the same. So is it like a discrete jump that, I get it when you cool it enough and it becomes like a gas to liquid and then to solid, there's less possible configurations, but what about like within the same state of matter?
Yeah, I mean, so if you think about this, like this, when we talk about the number of possibilities, we usually think about things in terms of, like, let's say, position and velocity. Like, if I have, let's say, just one particle, right, then its position and its velocity determines its state, essentially. So when you bring the temperature down, as you said, you basically remove certain possibilities for what its velocity can be. And in that way, you're reducing the number of possible states or configurations that the particle can be in just by lowering its velocity.
I see. That makes sense. So Tim, are you basically saying that if I go to absolute zero, it's like theoretically minimum possible temperature, that your entropy will essentially be zero?
Yeah, originally that's what people thought. And this is, I think, roughly the statement of the third law of thermodynamics. I mean, people are very familiar with the second law. It says entropy always goes up. But there's actually a third law of thermodynamics that says that if you just take a system and dial it down its temperature lower and lower, eventually you're going to reach some minimal entropy state. And it kind of makes sense, as you remove the currency of the system to do stuff, eventually you tend to just go into one particular configurations. And that people used to believe that is the lowest entropy state, and there's only just and people believe that there used to be just one possibility, so the entropy is 0.
So okay, so if you're at this theoretical absolute zero, everything is quote unquote like frozen in place. So there's only one possible configuration. The entropy is basically at its minimum. Am I understanding that correctly?
Yeah, I think so.
Okay.
Yeah,
Great.
it's not quite 0 though, because we said like, like let's say that I have just like one type of particle and they're all frozen in place, right? I can exchange any two of them. And then if they're truly identical particles, then exchanging any two of them will give you the same state. But that is the theoretical minimum, but not necessarily 0, because there's still some enumeration of possibilities that can happen.
Gotcha. Let's suppose just to kind of take this to its logical conclusion, say all of them were absolutely different. You could tell them apart, and you were at 0. Then entropy would be 0. Is that correct?
Then it'll be 0. Yeah.
Okay, great. All right. So I think this nicely segues into our into the next thing I want to talk about, which is where quantum mechanics plays a role into this. So we briefly mentioned in the previous episode this, wave duality nature of particles and how you can think of how entropy relates to that. So I wanted to kind of touch upon that here for people who may have not listened to the past episode. Maybe we can give a high-level summary of that. So I guess, Mikey, I'm going to point put you in the
Whoa.
All right, fine, Tim. I'll put you in the hot seat.
No, I think, yeah, I'm not. This is not I think Tim knows a lot more about this than me. I think Tim's gonna.
Well, I guess we have a pretty good intuitive explanation. So without quantum physics, when we talk about particles, we tend to talk about particles as an infinitesimal piece of dust, right? And so even if you freeze it in place, there's still kind of an infinite number of possible ways to put the location of the dust, So kind of in fact, the number possibility is kind of ill-defined because particles in conventional physics is infinitesimally small. So you can't really count. The number possibility is always infinite. But in quantum physics, people start to appreciate that particles are actually waves. They're not actually point-like. That means that imagine you have a box, right? And when you cool down, let's say the air molecules in the box, or whatever molecules, they'll actually form a wave and spread out and fill the entire room, basically. Like the entire quantum mechanical wave will fill the room. And depending on the shape of the room, there are only very specific discrete shapes that it can fill up. And in this way, quantum physics kind of makes entropy well-defined now, because you can literally just count using your fingers, like how many shapes will exactly fit the room that these particles are in.
So I guess one thing we want to mention to the audience, just to align on definitions, is entropy can be thought of as a number of configurations, and if you think of it in terms of this quantum mechanical way, what you're saying is that instead of thinking of it as particles, thinking of it as waves, and the more spread out it is, would you say like the less entropy in some sense? Because there's less number of wiggles, or how do I think about that?
Yeah. Basically, there's a theorem. I think mathematically you can show that if you have a quantum mechanical system and it has the minimal amount of energy, right? You can show that the shape of the wave this occupies has to have basically no wiggles, right? It cannot go up and down, up and down. No, it has to have a minimum amount of wiggles. So that fact is true. So given any shape, and according to the mathematics, you can a lot of times you can prove that there is just one shape that fits in. There's like one Goldilocks shape for the wave to fit into whatever shape of your system.
Is there a way you can give an analogy to this with water waves? Like, say I had a box, filled it with water, and and there's some amount of energy in the water. How can I think of it in terms of water waves as an example?
I think it's better to think of it as an instrument, right? Like imagine you have a guitar,
a
right?
violin string.
Yeah.
Oh yeah.
Or more like a guitar, right? Because the lowest energy state will be like the lowest note. Like every guitar has the lowest note. I mean, if you don't have a node, you don't even have stuff to begin with. So the zero entropy state will be the lowest note possible, and that would be, I don't know, like for a standard guitar, it's like the low E or something.
Yeah.
I'll take your word for it. I don't play guitar, so
Well, I guess the idea is that like once you can determine the energy of a particle essentially by the number of wiggles in the wave, now you can start to count how many wiggles there are. There's like the lowest note a guitar can play is when the whole string is just vibrating, right? And then when you put your finger down on a fret, now you have like 2 wiggles, and you put, the more fingers you put down, I guess the shorter the wiggles get. But just the fact that like once you think about it as a wave, now you can count the number of wiggles and use that as like a discrete number with which to kind of count entropy.
Gotcha. Okay, so entropy is dictated by the number of wiggles. The number of wiggles is also dictated by energy. I assume that if you have more energy, you have more number of wiggles, right?
Yeah, more possible wiggles. Yeah.
Yep.
Okay. So now if we imagine like the lowest energy state, how do I think about that in terms of entropy? Is it zero? Is it non-zero? What is this bound? Or is there a bound universally, or does it depend, or what are your thoughts?
I think in the beginning, people tend to think that at the lowest energy, there is only one possibility. There's only one note you can play. But slowly, people come to realize that, hey, it's actually not that simple. Depending on your system, some systems actually have multiple possibilities. And I think in material science, one typical example is what we call frustrated system. We can explain why. And we can explain why it's so frustrating just in a second.
That's a really interesting name. I do want to delve into that. I guess like, are you saying that like, okay, so if I look at quantum mechanically, there are these different states of energy. You can like, the higher the energy, the more wiggles there are. And then the ground state is like a specific state with the lowest energy. So if a system is in the ground state, it seems like there's only one possibility, but you're saying that's not quite the story. What gives with that? What's going on with that, Tim?
Yeah, I mean, for a lot of systems that people just come up on a whim, it seems like, yeah, there's only one possibility. But it turns out that there are a lot of systems where there is something what we call degeneracy, meaning kind of multiple possibility given the same amount of energy. And this situation is like, for example, imagine you flip a coin, right?
Mm-hmm.
Let's say it doesn't matter if it's heads or tails. You get the same amount of money, right? Let's say money is energy. So then you know that, hey, heads or tails doesn't matter. Then already there's two possibilities. And it turns out that nature is filled with these. And for example, one of the really typical property that particles tend to have is spin. So electrons have spin. You can think of them as kind of ups and downs, kind of like flipping a coin. And sometimes the energy of a system doesn't care the spin of the electron. And that means ups and downs are the same. So depending on flip of a coin, it all of a sudden you get multiple possibilities for a system. Ups or downs, same thing. So that's kind of one of the most basic ways to have multiple ways of having the ground state or a non-zero entropy, I guess, at the lowest energy.
Yeah, and this kind of relates back to what I was saying before. Like, if you imagine you have like 100 identical particles that are all frozen in place, if they're truly identical, you can swap any two of them, and you can't tell the difference. And that's another example of what Tim described as a degeneracy.
Gotcha. So what you're saying is that even at the lowest energy, there are certain properties of the systems or individual particles that where the energy is not impacted by those properties. They can be whatever they want. And because of that, it creates multiple like different multiple ground states that are all these different combinations of these properties. And that's what gives rise to this thing called degeneracy, which is multiple ground states corresponding to the same lowest energy.
It doesn't have to be ground state. It's just like any it's the idea of multiple equivalent states, where you have multiple states. That doesn't necessarily have to be the ground state, but if you just have a bunch of configurations where you have more than one that are equivalent to each other, like you can't tell the difference between them in any way, shape, or form, then yeah, that's what we would call degeneracy, and that gives rise to entropy.
I think a good analogy is like poker. If you guys play poker, right? Like if you have a pair of ace, doesn't matter what the suit of the ace is, you're gonna get the same amount of money, right? Or like
Wait, it
blackjack.
doesn't matter? Suits don't matter in poker?
I don't think so. Yeah. Or if you play blackjack, right? Like if two players get the same, get blackjack, they win the same amount, right? So like there is a degeneracy on different types of blackjack or flushes or even royal flushes. There's degeneracy, right? So it's pretty prevalent.
I need to Chinese poker where the suits do matter.
All right. Yeah. I mean, I think from Texas Hold'em, they don't matter as much from my scant memory of it. But yeah, I don't doubt what you're saying, Mikey, about the other variation. Yeah. So I guess the next question I wanted to ask, so we've covered degeneracy, multiple possibilities corresponding to the same energy. I wanted to ask about like, why is there a minimum energy to begin with? Like, first of all, like, can it be zero? Can it even be less than zero? And then why is there a minimum? Why can't it just like go down to like, I guess just keep going down? What's going on with that? These
like to negative numbers?
Yeah, negative numbers are just like sort of like keep jumping down. Why is there like a minimum inherent energy when I first learned about quantum mechanics?
Yeah, I think that there are quite a few questions here. I think first of all, conventionally, the zero energy is a convention, basically. The lowest energy is treated as a zero energy, so that anything on top of that is positive energy. Of course, in most of everyday life situations, only the energy difference matters. So the absolute amount of money doesn't matter as much. But that is unless you take gravity into account, because gravity is absolute, it turns out, because energy itself can create gravity. So it does matter whether you start with zero energy or negative energy. So to answer your question, yeah, energy could be negative because, as we have described before, negative energy could be associated with negative cosmological constant, kind of like I forgot, is it anti-gravity or expansion? Oh, but I don't remember anyway. So there is energy could go negative and positive, and it does matter, but only when you include gravity.
I see. And anything you want to add to that, Mikey?
Yeah, I don't know. The whole like it's a really sticky topic, I think. This idea of like, because if you imagine, like, people often, like, when we learn physics at first, we think about a ball rolling down a hill, right? And physics teaches us that the ball will always settle at the lowest energy point, right?
Yeah.
But if you're allowed to use negative numbers for energy and it's always going to settle at the lowest point, then yeah, it brings up a very good question, like what stops this thing from just going down to negative infinity? And I don't. We've talked in the past about how like there's no such thing as infinity in physics. Everything we measure in nature has a finite quantity. We don't believe that nature is capable of producing infinities. So I don't know. I think this kind of leads to a picture where just imagine if you can only deal with positive numbers, then you do have a minimum, which is zero, and then you can always just like, and as Tim mentioned, there's some ambiguity in terms of how you define energy in terms of like relative or absolute. But I think the typical convention is just to figure out what the lowest possible theoretical value is and just assign that number to be zero. And then everything else from that is positive. And then you're good. Then you don't have to deal with these negative infinities or positive infinities. And I don't know, that's not a really good answer, but
I guess can we discuss like maybe I guess maybe more textbook example of like why is there, what if quantum mechanical systems like an atom, you could have energies that keep getting less and less and less, things like that. Like,
yeah, no, there are theories where when I think of a ball rolling down a hill, people have constructed theories where maybe the hill just keeps going down and down and down and down and down. I think the main reason we don't believe those theories is because if those theories are true, then the universe would blast itself apart. So there's like some physical reason to believe that there is like a lowest energy state, and there is like a minimum to what you can measure the energy to be. It's not a rule. It doesn't have to be that way. But if it wasn't that way, then we wouldn't be here. So I don't know. I think we kind of accept that. I don't know, Tim. What do you think of that?
Yeah, I think it's a bit of a conventional wisdom, right? Like if there is no bottom, then it's kind of like a bottomless pit. Like because quantum physics tells you that anything that could happen could happen. Then you can almost like keep borrowing energy from the future, and the system might just keep tunneling lower and lower and lower, and it's kind of like a endless hell of like descending into you know an infinite pit of debt. It's like you can borrow infinite money. So physicists don't like that, and pretty much in all the system we've studied, nothing like that has ever happened, right? Usually a lot of systems
we don't like it, right? It's like if there was no bound to the minimum amount of energy, we wouldn't be here.
Right, yeah. Right. We would have just decayed away. So
yeah.
So at least approximately in the near term, in the millions of years, like there's going to be an approximate floor. If there's something lower, it will be so inaccessible that the universe hasn't completely fallen apart yet, basically.
And by the way, it's worth mentioning that especially especially with like the measurement of like the mass of the Higgs boson, it really calls into question like our universe might be temporary. We might not be at the floor. Like it's possible that in some number of years we will transition into some state with lower energy, and then we'll all just be blasted apart like instantly. So it's
very
a
optimistic.
reasonable fear.
Very bright and chirpy news, Mikey. Yeah, so I wanted to now come to the main enchilada of this episode, which is this inherent contradiction, or at least seems a contradiction to me. So we've discussed in a number of episodes about the universe expanding, and as it expands, it seems to get colder and colder. Like if you rewind the clock back, universe was much, much hotter. Now it's like getting really, really cold. And based on our discussion today, it seems like as things get colder, entropy should go down. But second law of thermo states that entropy should be going up. So which is it? Like, is it going up or is it actually going down? What's going on here? I guess, Tim, I'll put you in the hot seat since Mikey didn't like being put in the hot seat last time.
No, it's not just that. That's a very tricky question you're asking.
Yeah, it's actually a very tricky question. And if you just Google the answer online and people just give you some very simple answer. And this question turns out to be actually very, very deep. So the conventional explanation is this. Sure, if you look at a fixed area, as the universe expand, and then you see that, hey, like entropy is going down because it's colder. But then it seems a little, I don't know, like it seems like a little bit wrong, because as the universe expand, the area that you're considering should expand with it, right? So you naively just follow, imagine you draw a circle and you say, hey, as the universe expands, this circle will also expand. And you look at all the total possibility, it seems like the possibility will increase. So even though that possibility gets so diluted, such that if you zoom in and you look at the small area, yeah, it's true that temperature is going down and down and down, and it's going to absolute zero. That region will get lower and lower entropy. But if you sum up all the areas, the exponential of the universe eventually will become exponential, right? Mm-hmm. So that these regions will get so large. So if you sum up the tiny bit of entropy in every little small region, and you add them up the exponentially large amount of volume, and you'll probably see that, well, if you sum them up, yeah, even though locally entropy goes down, the total entropy will probably increase. So that's the naive answer that says, hey, look, maybe there isn't contradiction after all. Because you just need to zoom out and look at the universe from a bird's eye perspective. Then you wouldn't see this contradiction.
Mm-hmm. I mean, yeah, just zoom out, man. That's all you need.
Why is that naive?
Because you can't do that, unfortunately. I think we got to describe this. There's a dogma in physics that says that if you cannot, in principle, observe something, then it might not make sense to talk about such a thing, right? And I think to do that, we have to talk about the notion of a cosmic horizon.
Okay, let's talk about it. What is a cosmic horizon, Tim?
Yeah, basically, it gives you a limit. Like, imagine you're an observer in the universe, because, like, look, the way I'm talking about it is as if there's like a bird's eye view, like a God's point of view, to look at to be overseeing the universe. Well, you can't do that, right? Because physics is an experimental science. Imagine me as a physicist trying to confirm, I don't know, Sahil, your explanation that, hey, look, entropy should go up at the end of the day, right? Then I stay in the universe. I get all my experiments out there. As my universe expands, at some point, there's a boundary at which I can no longer detect things outside of that, right? Because as the universe expands, at some point, things are going to expand so fast that it's going to be faster than the speed of light now. And I can never grab them anymore.
Can we, Tim, can we quickly go over this expanding universe in terms of how it depends on distance away from you? Just like really, really quickly.
Oh yeah, I can do that. Yeah. So like,
perfect.
like we like to think that our universe is expanding, right? But there's actually a weird sense in which our universe is actually shrinking. So the standard explanation for why our universe is expanding is because space is stretching, right? So let's say there's a star like a million light years away, right? If space is just stretching uniformly, then that galaxy that's a million light years away is moving away from me at a certain rate. But if I look at a galaxy that's 2 million miles away from me, 2 million light years away from me, that's moving away at a faster rate. So one of the consequences of the idea that space is stretching is that things that are farther away are moving away faster. And that means that if you look far enough away, you're eventually going to see things that are moving away faster than the speed of light. And since we can't communicate with any object that's moving away from us faster than the speed of light, it literally puts like a hard boundary. Like, I know, to me, that's the shape of the universe. The shape of the universe is a sphere around every single person, beyond which things are moving away faster than the speed of light. And if you imagine that the acceleration of the universe, the expansion of the universe is accelerating, then things that are moving away faster than the speed of light, that boundary is going to get smaller and smaller and smaller until the point we get to the point where like even you're moving away from me faster than the speed of light. So the regions of the universe that we have access to, if you assume that the universe is accelerating in its expansion, which we have experimentally verified to be true, then the regions of the universe we have access to will be shrinking steadily with time.
That makes sense. Okay, so there's a certain like sphere that I can draw around myself for you, which is a thing called cosmic horizon. And anything like at that boundary or beyond is moving either at the speed of light or greater away from me in terms of the space itself expanding, not necessarily the thing itself moving.
Yeah, exactly.
Yeah, and I think a good visual in mind, it's kind of like a black hole, but like inverted in some ways, right? Like imagine I have this cosmic horizon, and I, let's say, toss my favorite toy at it really hard, so it flies away, and at some point it reaches the cosmic horizon. I can never retrieve my toy anymore, basically because as it flies away from me, as the universe expands, at some point the toy I threw away is going to be moving faster than the speed of light. And because the universe is going to expand even more and more and more, I can never get it back now. So it's very similar to the conundrum of a black hole. It's almost like the thing I toss away is just gone. The information of it just completely disappears, right? Because I can never retrieve it. So if entropy is counting the number of possibility, it looks like that possibility has gone. Right? So very intuitively, the fact that the universe is expanding means that the sphere of possibility is shrinking with respect to me. So it looks like, hey, possibilities are actually shrinking. Like it means that entropy is decreasing. If I try to measure it, if I try to measure entropy in my own little observable universe, entropy is decreasing.
And this is very much connected to what we were talking about before, that like as the universe expands, you have temperature going down, so entropy is also going down. Are those two related to each other, or are they like two different things that end up having a similar conclusion?
Yeah, I think that those are two things that end up having similar conclusion. Yeah, for like.
Okay. Mikey, were you going to say anything? I don't know if I
No, I,
interrupted you.
I intensely wanted to know the answer to that question, so I was listening. I just put my head in closer.
All right. So Tim, you mentioned this word now we've defined, cosmic horizon. What does this have to do with the contradiction? Like how does this play a role in that?
Yeah, so basically, I mean, let's reiterate, right? On the one hand, entropy should always increase, right? And it should be measurable, right? But then on the other hand, in a very real way, in an expanding universe with an accelerated expansion rate, we see the entropy decrease. Okay, so these are two contradictions. And now there's a third thing, because we know that in quantum physics, possibilities don't just disappear. So whatever I toss away, the possibility should remain, right? Even though I toss it away, even though I toss my toy away, or there should still be some evidence of it left, you know. So the quantum physics also says that the possibilities should not go away, right? But then at the same time, the area that I can observe is shrinking and shrinking and shrinking. So really, the question is, which one is it? Is entropy increasing, staying the same, or decreasing at a cosmological timescale?
It seems like, based on what you're saying, by quantum mechanics, it seems like entropy is staying the same because you can't lose possibilities. So does that mean that quantum mechanics is wrong, or like what? Yeah, I pose that question back to you, Tim.
Thank God.
And to be honest, I don't know what the answer is, and and that's why I say, you can find a naive answer, and the naive answer is that, hey, entropy increases if you consider the entire universe, ignoring the cosmic horizon, but it's not measurable. And in fact, this paradox was outlined by Leonard Susskind in one of his papers in 2021.
Best paper ever. Not best paper ever.
And unfortunately, this is very similar to the situation of black holes. It's the statement that when you toss something into the black hole, does that thing stay or does it go away? And you know that in a very similar vein, black holes also shrink ultimately because of Hawking radiation, right? So it's like, as the radiation, as the black hole radiates and the horizon shrinks, okay, like does the information stick around, or does it go away, or what's the resolution? So we have a very similar scenario, right? We have a horizon, somewhat similar to the black hole horizon, not exactly the same. And maybe information is stuck on that surface, and that surface is not static, it shrinks. So where does it go? I don't have a good answer. So I really don't know.
Okay, let me play Sahil for a second. So then, like, if we're to assume that the resolution to the black hole information paradox is similar to this, then does that mean that the information is captured like in the Unruh radiation on the boundary of the universe in some weird subtle way?
Yeah, but I mean, for black holes, the radiation kind of returns to you, but for us, the radiation still escapes us. So it's not like, it's not like I toss something to the cosmic horizon and somehow there's radiation coming back to me. That doesn't happen, right?
Mikey, could you re-explain your question? So I just want to make sure the audience is following with what your question was about.
Oh shoot, yeah, I wasn't thinking about that. I mean, just like there's an analogy, like, so Hawking radiation. Oh man, we shouldn't even get into.
Just
Shouldn't have asked that question.
super high level, or I can try taking a stab. So black holes radiate photons, and what you're saying is if you throw something towards a black hole, the physics states that it'll, like, if you're from viewing it from the outside, you'll see it slowly approach until like it just kind of plasters itself on like the event horizon, the surface of the black hole. And then
Yeah.
eventually, if you wait long enough, I mean, that all the particles and the structure of it will get pretty much scrambled by the black hole, which we've talked about in a previous episode, and that
Yeah.
will get radiated away through Hawking radiation. So your
Yeah.
question was that if you throw something towards the cosmic horizon, will it essentially plaster itself on the cosmic horizon and radiate away similar to a black hole? Is
Well,
that
kind of,
fair?
yeah, that was kind of my question, but like, I guess my question just goes a little step further, which is with the black hole, like, even though you see things plastering against the horizon, if you actually measure the radiation coming out of the black hole, the
Hmm.
standard lore says that you should be able to descramble that information and get back what you got in. And so my question was like, if you throw something into the cosmic horizon, is there a form of radiation that comes out that you can use to descramble what you threw in there?
Hmm. Yeah, I guess Tim is saying no because there's no like analog of radiation going because we're like on the inside in some sense. So this is like
Yeah.
I don't want to say reverse black hole or we're on the
No, I
inside
think that's
of
fine.
black hole-esque like structure.
Hmm.
Yeah.
Yeah, and I think
Okay.
the resolution might just be that this counting of possibility is probably really subtle. Like we're probably not counting everything properly, right?
Mhm.
And probably whatever you're doing inside this inside our cosmic horizon is probably what we call entanglement, meaning there's some correlation with what happens outside. So there's maybe a duality between what happened inside and outside. When you count all the possibilities, it's really hard, right? Like what's happening inside has some information about what's happening outside and vice versa. So
Mhm.
I don't know. I mean, in Susskind's paper, he didn't provide a resolution either. He's basically saying that something is wrong. We don't know which one. My money may be on the second law of thermodynamics. Maybe entropy doesn't always go up. Like, why do we insist on that? But who knows?
Yeah, no, that's a fair point. I guess so now kind of coming back to this full circle. Oh, Mikey, were you gonna say something?
No.
Okay. So coming
Talking
back
about
to this full circle, we talked about classically that if the second law of thermoentropy going up, we talked about this cosmologically and based on like your own observer frame of reference within the universe, you see entropy going down cosmologically. Where does that transition happen? Like if we look at counting number of possibilities, like why is the universe different than like the systems that we have? Kind of like tying this back all together, just sort of
I think, I think the crux is gravity. Gravity is always the
not
troublemaker.
horizons are the troublemaker, right?
Right,
And,
sure.
well,
Yeah. So horizons are created by gravity, and all that is because of relativity. Because there's a cosmic speed limit, right? There are boundaries. There's an ultimate speed limit, which kind of chunk the universe in a really weird way, right? And there's this law that gravity and quantum physics have conflicts, and this is where the conflict lies, really. Quantum physics says that information must be preserved. There are many different names for this. It's called unitarity, preservation of information, and things like that. And it tells you that, hey, things, even though they might appear to be going away, they never truly go away. And that's a central dogma in quantum physics. In gravity, it says, well, things could go away if they move, if they, because there's a cosmic speed limit. The speed of light is the limit, right? You can't instantly grab, a star from a nearby galaxy. You can't. They're really far away. So I mean, this conundrum is just the conflict, the head-on conflict between gravity and quantum physics.
Yeah.
I see. There's a question I wanted to ask based on what you were saying, but now I've completely forgotten it. It's went out of my head. Okay. So essentially you can there's inherently a speed. Oh, now I remember my question. So, we've talked about expansion in the universe and gravity, but I just want to clarify for the audience, like the difference, not the difference, but how these two things are related, because it seems like expansion of the universe and gravity seem opposite to each other. Gravity attracts things. Expansion of the universe seems to be this like repulsive thing, or I don't know if I want to call it repulsive, but like has a different, it seems like moving in the opposite direction of gravity. What you learn from like classical Newtonian physics from like high school and whatnot. So how do you, when you say gravity, Tim, why is this related to gravity?
Yeah, because I mean it is to some extent anti-gravity, and this is the famous what Einstein called his blunder. It's basically a term called the cosmological constant, and the origin of this is quite unknown. Einstein originally proposed this because he noticed that gravity is attractive. Okay, if you only have attraction, the universe might eventually form a crunch, right? But Einstein didn't like that, so he put in an extra term to kind of balance that out. He's like, hey, look, maybe the universe have existed forever. It shouldn't just destroy itself. So he added an anti-gravity term to balance that out, and this term roughly gives you kind of like a repulsive force, like a universal propulsive force. And later on, it turned out that we measure this universal repulsive force, and it turns out to actually be overwhelming every other gravitational force. So at the stage of our universe right now, we are at the cusp of this repulsive force overtaking the evolution of the universe. So yeah, even though in high school physics, in college physics, we talk about, hey, gravity is attractive, but that just is because of the state of the universe right now. It turns out that there is a universal repulsive tendency, and we're just starting to see its impact on the universe. And in many, many eons from now, that will be the biggest force in the universe.
Yeah, and just to add to that, I just wanted to point out that it's amazing that quantum mechanics itself predicts this repulsive force. Because quantum mechanics, as we mentioned in many previous episodes, it predicts that empty space should have its own minimal amount of energy that it can contain. The energy of a patch of space can't be zero according to quantum mechanics. And directly from Einstein's theory, this also implies that, Einstein's theory implies that any kind of minimum amount of energy that's intrinsic to space and time will cause a repulsion. So gravity is just weird. When you look at Einstein, we think of gravity as just an attractive force, but if we look at Einstein's theory, it predicts that certain types of matter will cause attraction, and certain types of energy will cause attraction, and certain types of energy will cause repulsion. And there's this whole interplay between those two things that kind of determines the cosmic history.
Very, very interesting. So we're almost at time. So I wanted to give you guys a chance to leave the audience as usual with any words of wisdom from minimum entropy now instead of maximum. Mike, I'm going to put you on the spot this time since I know
Yeah, I mean, I don't have much to say about this other than the fact that people talk a lot about the conflict between quantum mechanics and Einstein's theory of relativity. And I would just like to echo what Tim said, that I think this conundrum, this kind of seeming paradox that we're talking about right now, I think really cuts to the deepest part of this. And it really relates back to the idea that gravity creates horizons. And a horizon, just to reiterate, is basically a surface where I can't see past. I have no access to. It might as well not be part of my universe. And when you create these horizons in the universe, it really messes with your conception of what is possible in physics and what is not. And this is physicists over especially the last 10, 15 years have had to completely kind of rethink their conception of what cosmological physics looks like in light of the existence of these horizons.
Yeah. I guess I would like to add that physics is, it's a very much alive discipline. I mean, physics is kind of one of the core tenets of science. We are at the boundary of scientific discovery and research, right? And part of that means that a lot of the laws that we believe were sacred are probably not sacred. Like, for example, in this episode, we mentioned the second laws of thermodynamics, which, if you ask a lot of physicists, they might be like, hey, this is probably the one that I'll bet my money on will never be wrong, right? But yet, if you take the second law of thermodynamics, you add in one of the very sacred laws of quantum physics that information should always be preserved. And then you add in Einstein's laws of relativity that the universe expands, and bang, when you combine them, they just don't like to be combined, right? There is a contradiction. So one of them has got to be wrong, right? So I would just caution that, like, in physics, a lot of these principles we hold dear and we believe are the ultimate truth. Well, some of them probably are not. And sometimes things might be a little more surprising than you think. So I would say that like when you go online, there's a lot of, like, perhaps naive explanation that seems very plausible. Maybe it seems right, but the reality is far more complicated. And in this case, we actually don't know what the exact answer is. Which one of these law is wrong? My bet
subtle, not complicated.
Yeah, I guess so. I guess. My money.
It's never complicated.
My money is probably going to be the second law of thermodynamics. I was never a big fan of it anyway, but make your own judgment.
Yeah.
Well, yeah, I mean, I probably would bet money alongside with you, Tim, on that one as well. Yeah, so on that note, I want to thank everybody for joining us, and we'll see you all next week.